Today, we're going to be talking about neurons. Neurons are the basic building block of the nervous system. The picture here is actually a statue of a neuron, which I love. It just shows how wild and crazy neurons are. You actually have billions of neurons in your body, and what they do, they actually send messages to each other. All right, so everything you're doing, that message is being sent by a neuron. So next unit, when we talk about development, we're going to talk about how when babies, it's very important for them to touch different textures because every time they touch a different texture, that's a new neuron that's being sent, and they're making new networks. You see these little branch thingies coming off at the end? Well, each of those is connected to another neuron. Not technically, there's actually a space in between, but there's this connection, and you want as many connections as possible because then you can think faster, your reflexes are faster, and you just kind of know more things. So this unit is going to be extremely important to understand the anatomy of a neuron. So first we're going to talk about dendrites. Dendrites, that's what I was just showing you. They receive the message. So like I said, how neurons send messages. The dendrites receive the message from another neuron. Then you have the soma. The soma is the cell body. And that's right here. This thing right here. It's the cell body which houses the nucleus. The nucleus is inside here. This is what processes the information. So this is like the brains of the neuron. All right, so whatever message is being sent is being processed, so you're understanding it through the nucleus. Then the axon is what carries the message. That's this long thing right here. Carries the message. You have the myelin sheath that wraps around the axon. The myelin sheath insulates and protects the axon. So the myelin sheath is made up of glia cells. The myelin sheath actually speeds up the information. So people with certain diseases like MS, their myelin sheath is actually breaking down. It's not functioning correctly, and that's why they have some of the issues that they do. And then at the end, you have these terminal branches here, and at the end of the terminal branches, you have terminal buttons. All right, so terminal button sends messages across the synapse. So like I was saying, no actual neuron touches another one. There's always this gap in between. That's called the synaptic gap. All right, the space in between the axon tip and dendrite cells of another one. And so there's something called a neurotransmitter, which we'll talk about, and that's the actual message being sent. So it travels down the axon branches to the to the terminal branches, then to the terminal buttons, and then the neurotransmitter is released across that synaptic gap, and then it connects to another neuron, and then that one fires, and then the next one fires, kind of like dominoes, which is a little metaphor we'll talk about. So a picture of a neuron a little up close. We have the cell body here, which is the cell's life support center, right? So we talked about how we have the soma, and then we have the nucleus inside, which processes everything. You have the dendrites out here, which receives the messages from another cell. Remember, you got all these dendrites, connected to, billions of different neurons. And some of these dendrites and these neurons can actually be extremely long. You have the axon, which passes messages away from the cell body to other neurons, muscles or glands. Remember, that's covered by the myelin sheath, which protects it, insulates it, and helps send the message quicker. So the message helps speeds the neural impulse, which is the electrical signal traveling down the axon. So this is also called action potential. So you actually, when the message is being sent, there's actually a little electrical charge that's happening there. And then we talked about how you got the terminal branches at the end, and at the end of each terminal branch you have the terminal buttons, and then the little gap before the other neuron is connected to it. So how a neuron fires is pretty much 3 steps to neuron firing. The first step is the threshold is reached. So the axon is sitting at resting potential. That's a vocab word, make sure you know that, which is the fluid inside the axon is mostly negatively charged with positive on the outside. This is called polarization. All right, so it's called polarization. So resting potential just means it's sitting there and the neuron is ready to fire. It hasn't fired yet, it's ready to be able to fire. So an impulse is triggered in the neuron's dendrite, when stimulated by pressure, heat, light, or a chemical messenger from another neuron. So the stimulus threshold has been reached. All right, so that means that the neuron is going to fire. So for the neuron to fire and the threshold has to be reached, you have to be aware of something. So let's say if you ever like touched, someone's shoulder and they couldn't feel it, well, that threshold wasn't passed yet, so those neurons didn't fire. But once they actually feel, them being touched, that means a threshold has been passed and the neuron is now firing. So step 2's action potential begins. When neurons fire, its axon membrane is selectively permeable, which means it actually has gates in it that open up and let the ions in. So gates in the axon called ion channels open, allowing positive sodium ions to enter the axon, giving it a brief positive electrical charge to the axon. So it becomes depolarized. Remember we talked about how all the positive ions, the sodium ions were on the outside and the negative were on the inside. Well, when the neuron has passed its threshold, so you can feel that touch or hear or smell or whatever the sense might be, all of a sudden these gates open up and the positive ions come rushing in and it depolarizes everything. And with the ions mixing, the positive ions mixing with the negative ions, and the negative ions are being pushed out as well, this gives a brief positive charge. This is called action potential. That's what I was talking about on the other side. That neural impulse, that electrical charge, is called action potential. Right? So when it's just sitting there, it's polarized. When it's past the threshold and the gates open up, now it's become depolarized, and that's called action potential, that brief positive electrical charge. So you can see in the simulation how you have all the positive on the outside and all the negative on the inside. Once that, these dendrites receive the information processed by the nucleus, threshold has been reached, and the gates open up. Notice they don't all open at the same time, so it's kind of like dominoes. So this one over here can't fire until the one before it has opened. So this one opens, and this one opens, and this one opens, and this one opens, and so forth. And you notice that then it recharges itself. That's going to be step number 3. So all the positive ions have been rushing in. All right, all the positive ions rush in, all the negative ions then rush out. Well, then it becomes depolarized, but then it has to, get back to polarization. So then it pushes the positive ions that are inside back out and the negative ones back in, and that is going to be step 3. That is called the refractory period. All right, very important vocab word there. So as the next gates open, allowing the positive ions in, the previous gates close and begin to pump the positive ions back out, like we just saw in the simulation. This is called repolarization. This is called the refractory period. Now, if you look up refractory period in the glossary, you might get a different term. You're going to see that sometimes this year because some words have different meanings depending on what you're talking about. When we talk about refractory period in this class, we're only going to be talking about with reference to neurons firing. All right, and a lot of times when you have vocab to do, if you just look up regular, like the terms in dictionaries and not necessarily like a psychology textbook, you might get a different definition that has nothing to do with what we're talking about. So make sure you understand that. So the axon cannot fire again until it returns to resting potential, right? Which is a polarized state inside the axon. That is a refractory period. So as the gates open up and that neural impulse happens and all the positive ions come rushing in, that neuron cannot fire again until it becomes repolarized. That time period that it's recharging itself is called the refractory period. So why do you think the axon has to set itself back to a resting state so quickly? So it's able to do it within 3 milliseconds. All right, so the answer is that so a neuron can fire again and send another message immediately after the last one. So if you think about your body and your actions and what you do all day long, your body is constantly sending itself messages. And so it has to be able to recharge itself quickly so that neuron is ready to fire another message. So you can see this again here. You get the ion, the sodium channels opening up. So you have these positive ions come in. And then you have the potassium channels open and potassium ions rush out. All right, so the potassium are the negative charge going out. The sodium are the positive ones coming in. So the first sodium channels have closed, but those farther down the axon open, carrying the movement of depolarization along. And so that's just like the simulation we were showing before. How these ones open up before these ones can. And before these ones can, before these ones can. So just think about like a domino. And how like a domino, how, you know, the last one can't fall down to the one before it falls. That's just how the gates work on a neuron. And so this is, I think, the best metaphor for actually understanding the three phases of how a neuron actually works. So think about like a cannon firing, like the old school cannons, like if you study like U.S. history, like Civil War. So you have action potential, right? So the neural impulse created when a neuron fires. The impulse travels from the dendrite down the axon to the terminal branch, right? So you receive the message, right? So the captain is telling you to fire. So the guy lights the cannon and it sends the message. So it's that wick is lit, and then all of a sudden it lights off the gunpowder, shoots the cannon, which is the message, it fires. Well, the refractory period is that brief instant when a new action potential cannot be generated because the neuron is recharging after a previous action potential. So remember we talked about refractory period is that recharging where it repolarizes itself? Well, think about this cannon. This cannon can't fire again until you reload it, right? So it's being reloaded, you put in more gunpowder, you put in another cannonball, back down the cannon. All right, so that's a refractory period. You recharge yourself. Now you have resting potential, right? So resting potential is the state of a neuron when it is charged, but waiting for the next action potential to be generated. So now, if you see this guy right here, right? The cannon's ready. It's loaded. It's ready to be fired. It's just waiting for the command to be fired. And it's the same thing a neuron does, right? When it's at resting potential, it's ready to fire, right? It's polarized. It's just waiting for that command. It's waiting for that threshold to be passed, and then it can fire, and then it can do the whole process all over again. And I will post on the YouTube channel a video clip with the different parts of a neuron. So maybe that'll help understand it a little bit better. You know, there's two more parts to these notes. The neuron, to me, I think is one of the hardest things to actually understand this year. That's why usually I do a few different activities to help understand it. There's a lot of different simulations and metaphors we can do to understand the neuron. So if you're a little confused right now, don't worry. By the end, we will, get this concept, and that's why I probably spend the most time of any individual part this year on the neuron, so you have a good grasp of it.